Hello everybody, good evening and welcome back. So in the previous class we started a new topic, a new application of derivative, and that was monotonicity, and we saw that the monotonicity is nothing but the study of increasing decreasing behavior of the functions. And then we discussed the monotonicity at a point which can be described by the four standard terms, and those are strictly increasing, strictly decreasing, non-increasing and non-decreasing. We also saw the derivative test for the monotonicity at a point. And in today's class we are going to talk about monotonicity over an interval. Now you know that interval is nothing but the collection of infinite number of points, and if you have understood the monotonicity at a point, I'm sure you won't find it difficult understanding the monotonicity over an interval, right? So let's look at that. It has two simple points. The first one says that fx is said to be strictly increasing. I hope you remember this arrow up for increasing in interval a comma b, open interval a comma b, if f dash x, this is the important condition, if f dash x is greater than or equal to 0 and equality may hold for discrete values of x. Equality may hold for discrete values of x, and by the discrete values we mean that the points where f dash x is equal to 0 don't form an interval. They must not form an interval or collectively long or large number of points, which is interval only, right? So it is the simple point for strictly increasing. And the second point, again, fx is strictly decreasing if f dash x is less than equal to 0, and again this next condition is same, that equality may hold for discrete values of x only, right? So this point that discrete values of x, f dash x can be 0 and it should not form an interval, let me try to explain it to you with the help of an example, with the help of an graph. Okay, so consider this example. Fx equals x cube, whose domain is all real, that is x can take any real value, and if I look at its derivative f dash x, it is 3x square, and you can clearly see that 3x square is always positive or greater than 0 except at one discrete value of x, which is 0. So f dash x is always greater than 0, but 0 at only at x equal to 0, and that discrete value won't affect its monotonicity or its increasing behavior because this is always greater than equals to 0. Therefore fx is strictly increasing, right? So you can also look at its graph, and you are very much familiar with that. X cube, its graph is like this, and from the graph you can see that x cube is a strictly increasing function. Derivative is everywhere positive except at x equals to 0. Since the derivative is 0 at x equal to 0, you can check by the other things or other test you read in the previous class that if derivative is 0, we are going to check the sign of right hand derivative and left hand derivative, and you can see that 0 plus h square positive, and 0 minus h square, again h square positive. So right hand and left hand derivatives both are positive, therefore it is showing the strictly increasing behavior at x equal to 0 also, and at the rest of the points it is positive, so it is increasing there, right? So let me take another example to understand it more, right? So for example, let's say we have fx equals x minus sine x, x minus sine x, right? And if I differentiate it, f dash x is 1 minus cos x 1 minus cos x, and you can clearly see that cos is always less than or equal to 1, right? So this is always greater than equal to 0, but 0, that is f dash x, is going to be equal to 0 for x belongs to cos x is equals to 1 at 0, or you can say for 2n pi, ठीक है, right? N belongs to integer. Clear? So when cos x is 1, derivative is 0, but these values of x, which is 0, then 2 pi, then 4 pi, all are the discrete values. They are not forming any continuous interval over here, right? You can also see its graph also. The graph of x minus sine x will be like this. Here also f dash x is greater than or equal to 0. So therefore it is going to be strictly increasing function. Okay, so this is x minus sine x. Let me try to draw it. Its graph will be like this. And here is the point 2 pi, where derivative is 0, right? Again, you will get here another point where derivative is going to be 0, and that will be 4 pi. And on the left of the x-axis, that will be minus 2 pi and minus 4 pi. And you can see that fx is strictly increasing. Fx is strictly increasing at every point. Although the derivative is 0 at 2 pi, 4 pi, and that is not affecting its increasing behavior, because these are the only discrete values of x. It is not forming any of the intervals, right? So this is the example, two examples I try to explain the point we noted down, that f dash x may equal to 0 for the discrete values of x. Let me give you an example in which f dash x is 0 and it is forming an interval. For example, let's look at this. Here I am taking a random graph to show you this thing. Let's say okay. Now, here you can say that fx increased, then the derivative becomes 0 or the function became constant. When function is constant, derivative 0. So it is 0 for this entire interval 1 to 2. Again, over here also the derivative is 0 for the entire interval 3 to 4. So f dash x here is 0 and it is forming an interval. Therefore, this is not strictly increasing function. Then in this case, you will call it a non-decreasing function, because the function is not increasing. It is increased, then became constant, then increased, then became constant, and then increased, right? So I hope you understood the concept or the 2 points that we noted down. Condition only, that is strictly increasing when f dash x is greater than equal to 0, and fx is strictly decreasing when f dash x is less than equal to 0. The important was that the equality may hold for the discrete values of x. Now we will take some examples on this whole concept, monotonicity over an interval. Alright, so here is the first question. It says compute the intervals of monotonicity for the following functions. Intervals of monotonicity, by mean to say that you need to find out the intervals where the function is monotonically increasing and where the function is monotonically decreasing. The function can be increasing and decreasing. We need to find out the different intervals. Okay, so let's start with the first one. And you know, by derivative test it is very simple. Where derivative is positive, the function is increasing, and where derivative is negative, function is decreasing. Okay, so in the first example I have fx equals to this. Let's differentiate it directly. F dash x is going to be, we can apply the product rule, that is 2x into e की power minus x plus x square into e की power minus x into minus 1 by chain rule. And you can clearly see that e की power minus x is coming out to be common, and here what left is x is also common, and we are here 2 and minus x. So it is the derivative. We just need to check the sign. The sign will tell you increasing or decreasing. Positive sign means increasing, negative sign means decreasing. So let's go with the wavy curve. E की power minus x is always positive. X is 0 at 0, and this is 0 at 2, right? Because this is 2 minus x, so therefore the signs will be inverted in general case. Otherwise it would have been this curve, but in this case this is going to be like this, right? So here positive, here negative, and here negative. Okay, so I can see that f dash x is positive in 0 to 2, or you can say now that in interval 0 to 2 fx is increasing, and here, that is from minus infinity to 0 union 2 to infinity, where f dash x is negative, the function is decreasing, right? So this is our answer. Clear? I hope you understood that. Now let's go to the next one. You should try it by yourself and take a few minutes. I'm waiting for that. Okay, so I'm sure you all must be having some answers for this second part. Now let me do it for you. In this, f dash x is x, its derivative 1, then ln 4x, that is 1 upon 1 minus 4x and minus 4, right? So by taking the LCM, it is 1 minus 4x minus 4 upon 1 minus 4x. Okay, it is 4x minus 3, minus 4x minus 3. Taking the minus common from numerator and denominator, I can see that it will become 4x plus 3 divided by 4x minus 1. 4x minus 1. Okay, now the important point here is you should also take or consider the domain. Here the function is x plus ln of 1 minus 4x, and if I look at its domain, for this ln to be defined, this 1 minus 4x, it need to be positive, or you can say that x must be less than 1 by 4. X must be less than 1 by 4. This is the domain of fx. Okay, now let's check the sign of derivative for increasing and decreasing behavior. Here is the derivative, and if I draw a wavy curve, it is minus 3 by 4 and it is 1 by 4 here. The sign scheme says, right, positive, negative, positive. Guys, please do remember or do try to do some problem on this wavy curve sign scheme. Okay, so this we are going to use very frequently or almost in every question here. Okay, so domain was x is less than 1 by 4, that means this is not the part of domain. So on the left of 1 by 4 I can see that we have derivative positive for minus infinity to minus 3 by 4 and negative for minus 3 by 4 to 1 by 4. Therefore I can say that from minus infinity to minus 3 by 4 fx is increasing, and from minus 3 by 4 to 1 by 4 where derivative is negative, fx is decreasing. Okay, so this is the simple example on monotonicity. We just needed to find out the intervals of increasing decreasing behavior of the functions, right? So here we have another problem. Do try it again. I'm giving you a minute to try this one. Okay, so this C part is a little different because here we have this arbitrary constant A, so it may affect its monotonicity. So let's see what the derivative tells us first. F dash x is A minus cos x, right? Of course, now whether that f dash x is positive or negative, it will depend upon A. Now let's change the question a little bit, and let's say the question is find out the values of A, this arbitrary constant A, for which fx is increasing, and the second one for which fx is decreasing. Okay, again I repeat, the question now is for what values of A fx is increasing and for what values of A fx is decreasing. Okay, so let's do it one by one. For increasing, I know that f dash x must be greater than or equals to 0. Now here f dash x is A minus cos x greater than or equal to 0. I can say that cos x is less than or equals to A. Less than or equals to A. Now check for what values of A that this f dash x is positive or cos x is less than or equal to A. Less than or equal to A. Clearly you can see that if A takes the value 1 or greater than 1. If A is 1, cos x is always less than or equal to 1. If A is 2, cos x is always less than 2. If A is greater than 1, 1, 2, 3, 4, any value, you know that cos is going to be less than equal to this A, which is greater than or equal to 1. I am saying here, right? So clearly I can see that if A is greater than or equals to 1, this is going to hold true, this is going to hold true, or this is going to hold true. That is f dash x is going to be greater than or equal to 0 for all x, and I can say that fx is going to be increasing for all x. Alright, so here my answer is that A must be greater than or equals to 1, and this will make this function a strictly increasing function. Okay, similarly you can see for the decreasing behavior, if I need to check or if I want to make this function decreasing or strictly decreasing, I need f dash x less than or equal to 0, right? Or you can say that A minus cos x less than or equal to 0, or I can say that cos x greater than or equals to A. Cos x greater than or equals to A. Now for what values of A cos x is always greater than or equals to A? Just look at the minimum value of cos x. If I want to make a variable function greater than or equal to something, look at its minimum value. If I want to make a variable function less than or equal to something, then take the maximum value. here I know that the cos minimum value is -1, and if a is -1 or less than -1, then cos will always be greater than equal to its minimum value, which is -1. So a here must be less than equals to -1. Can you see or understand what I just said? This is a variable function. What I need here is a less than equals to cos x, which is a variable function. To make or to find out what value of a will make this inequality hold for true always, for less than equals to take the minimum value, for greater than equals to take the maximum value, and here our answer is a must be less than equals to -1. If a is -1, of course cos is greater than equal to -1. If a is -2, cos is strictly greater than -2. If -3, cos is strictly greater than -3, and so on, right? So second part of answer, that is for a less than equals to -1, fx is going to be strictly decreasing. Okay, so I hope you are getting these points. If you have confusion over here what I just did here, don't worry, don't panic. The more problems or more such problems will come later, and you will definitely get to understand everything I just said, right? So wait for that, please. For now, try this next part D, which is fx equals to x upon ln x. Okay, so let's first of all calculate its domain. You know that for ln to be defined, x must be greater than 0, and also it is in denominator, so it must not be equal to 0, and x must not be equals to 1. Okay, so x greater than equal to 0 and x must not be equals to 1. This is the domain of function. Now let's differentiate it to check the sign of derivative, or to see where it is increasing or decreasing. We have fx x upon ln x. Simply apply the quotient rule. Here I have ln x square ln x into derivative of x, which is 1, minus x into derivative of x, which is 1 upon x. So in simplified form I have ln x minus 1 upon ln x whole square. This is not equal to 0. I've already taken the condition that x must not be equals to 1. Again, now it is a square, so positive. So this numerator ln x minus 1 is 0 at x equals to e only. Okay, so we have only one 0, which is e. And if I look at the domain, I know that x must be greater than 0 and x must not be equals to 1. X must not be equals to 1. Now about the sine curve, when x is greater than e, this is greater than 1 or positive. Here it is positive and here it is negative, right? So this is where f dash x is negative and here it is positive. Now by looking at the domain and the derivative, I can see that for x belongings to 0 to 1, because 1 is not included, union 1 to e, it is negative, therefore decreasing, and from e to infinity it is positive, therefore increasing or strictly increasing, right? So this was an example on monotonicity over an interval, and in this particular question we were asked to find out the intervals of monotonicity or intervals of increasing decreasing behavior of the various functions. Okay, so I just want to tell you again that this particular problem, if you have any doubt in that, just wait for it. I will do some more problems based on this concept, in which there is arbitrary constant you need to find out for the condition of increasing or decreasing. Okay, so note it down. We'll do some more problems now. Okay, the second question here is, here we are given a trigonometric function fx as 3 cos raised to power 4x plus 10 cos cube plus 6 cos square minus 3, and you need to look in the 0 to pi where the function is increasing and where it is showing the decreasing behavior. Okay, and that is going to get only by derivative. So let's differentiate it. F dash x, here it is 4 3, that is 12 cos cube and cos derivative minus sign, chain rule. Then I have this 30 cos square x and again minus sin x, and 12 cos x and minus sin x. Okay, so what I can see that minus 6 or right 6 cos x and sin x is common. Here I am left with 2 cos square x plus 5 cos x and minus or plus 2, right? So here we have minus 6 cos x sin x, and this is a quadratic factor. Let's factorize this one. Minus 6 cos x sin x, and then its factor, what I can see is this will be 4 plus 1, so 2 cos x because I think okay, so factorize it for me. It will be 4 plus 1, so 2 cos x common, so I will be left with cos x plus 2 and the next factor will be 2 cos x plus 1, right? I hope I'm right. So it is 2 cos square x, 2 plus 2 right. Okay, so this is the right factorization. Now we have to look in the interval 0 to pi. 0 to pi, I can see that this is a negative sign. Sin x is positive in 0 to pi. This factor you can see here is cos x plus 2. You know that the cos minimum value is minus 1, maximum plus 1. So this is always positive. This is a positive value. This is a positive value. So these two are not going to affect the sign. What I am left here is this cos x, which is 0 at x equals to pi by 2, and this 2 cos x plus 1, that is, it is going to be 0 at x equals, it is minus half, so minus half, that is 2 pi by 3. 2 pi by 3. So draw the real line. Zero pi, here I have pi by 2, and somewhere here 2 pi by 3. 2 pi by 3. So let's look in these portions. Now in 0 to pi by 2, everything is positive, 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 but because of this negative sign, this will give you a negative sign, right? Now from pi by 2 to 2 pi by 3, this is positive, this is negative. Cos in the second quadrant is negative, this is negative. What about this? Cos at pi by 2 is right 0, but it will decrease to -1 at 2 pi by 3. Before 2 pi by 3, this is going to be positive. This is going to be positive. So this is positive, although this is negative, but because of this sign, this whole become positive. So negative, negative, positive, and everything else positive. So here I am having a positive sign of f dash x. Now in 2 pi by 3 to pi, let's see. Again, this cos is negative. This negative, negative is positive now. This is positive, this is always positive, and this will become now negative. So because of this negative sign, this will give you a negative sign. Clear? I hope you understood that how I looked in the various parts. First, I calculated the points of zeros, which is the basic rule of sine curve, sine scheme. This is 0 and 0 to pi at 2 pi by 3, that is 120 degree here. Then cos 0 at pi by 2, and rest everything is positive in 0 to pi. Okay, so now I think the answer is clear. That is in 0 to pi by 2 and 2 pi by 3 to 2 pi. Here the function is decreasing, also here decreasing, but here the function is increasing. Okay, so do write it in the interval form. We have the answer, right? All right, so here the next question is, it says is fx is, which is given as a plus 2x cube minus 3ax square plus 9ax minus 1 is always decreasing, that is decreasing for all x belongs to real. Find the value of a. It is the similar question we did earlier, that is in which ax minus sin x was the question, and you need to find the a for which fx is increasing or decreasing. Here we have been specifically told that fx is always decreasing. Okay, so we know that for fx to be strictly decreasing, its derivative must be negative or less than equal to 0, right? So let's check the derivative. Here I have f dash x equals 3a plus 2 x square minus 6ax plus 9a. By taking this 3 common, I have a plus 2 x square minus 2a x plus 3. Okay, so I need fx to be always decreasing, so therefore derivative must be always less than or equals to 0. Now derivative I have here is a quadratic expression. You know that a quadratic expression is always negative, or you can say that less than equal to 0. The condition is coefficient of x square, right? Coefficient of x square must be negative and discriminant must be less than or equals to 0, right? So these two conditions I need to apply here, and the first is a plus 2, it must be less than 0, and the second one is discriminant, which is 4a square minus 4 into 3 into a plus 2 less than equals to 0. Here 4 is getting cancelled. I am left with a square minus 3a minus 6 less than equals to 0. If you can factorize it, factors of this a square minus 3a minus 6. So is there any mistake or something that I can see is I think this is not giving us a good factors. So let me cross check if I can find a doubt or some mistake. So here was the derivative 3a plus 2x square minus 6ax plus 9a, and by taking 3 common, a plus 2x square minus 2ax plus 3. Oh, sorry. Okay, so what I missed here is 3a. It is a also here. So here there will be another a less than equal to 0, and so by cancelling out the 4 I can take 3a common, right? So 4a, and here is a minus 3a minus 6, okay, less than equals to 0, right? So what I have here is 4a, it is minus 2a minus 6 less than equal to 0, taking minus 2 common, minus 8a, and this is a plus 3 and less than equal to 0, right? So it's wavy curve. Please look at its wavy curve. This is a negative sign, and if I see its wavy curve, this will be like this, right? So the factors are minus 3 and 0. Because of this negative sign, the sign scheme will be like this, right? So here it is going to be positive, negative and negative. So this is giving us the sign scheme as a this, and from the first condition I have this a minus 2 negative, or I can say a less than minus 2, and by combining these two, minus 2 is over here, okay, you can see that I need a to be less than minus 2, and from here this required region is d and e to be negative, so here the d is negative, okay. So you can see the intersection part, less than minus 2 and less than minus 3. So clearly I have this part that a must be less than minus 3, or a belongs to minus infinity to minus 3. Minus 3 is the closed, because at minus 3 discriminant is 0 and discriminant can be equals to 0, right? So please trace out the whole problem, review it carefully. I made a mistake here that I forgot this a, so that was leading to a different routes, but by the correction I can clearly see these are the factors. Sign scheme, if you have not understood, kindly look closely. This is the negative sign, factors are minus 3 and 0, alright. So because of this negative, this is the sign scheme, negative, positive, negative, and the first condition was this coefficient making this negative, a less than minus 2, and from here I have a less than minus 3, and taking the intersection, because we want both of this to be together, we have here and sign, right? So all these things, little things that I'm talking about, wavy curve or the sign scheme, I hope you are very much comfortable with that, okay. So finally I am having this answer that if a is less than equals to minus 3, or it is from minus infinity to minus 3, this derivative will be always less than equals to 0, or the function will become always decreasing, okay. So guys, I am stopping here, and after a short break we'll be back with the more problems. We have various number of problems based on this concept, monotonicity, right? And later on we will add some more concepts also. So till then, do some problems, and I'll be seeing you very soon. Hello everybody, good evening and welcome back. So in the previous class we started a new topic, a new application of derivative, and that was monotonicity, and we saw that the monotonicity is nothing but the study of increasing decreasing behavior of the functions. And then we discussed the monotonicity at a point which can be described by the 4 standard terms, and those are strictly increasing, strictly decreasing, non-increasing and non-decreasing. We also saw the derivative test for the monotonicity at a point. And in today's class, we are going to talk about monotonicity over an interval. Now, you know that interval is nothing but the collection of infinite number of points. And if you have understood the monotonicity at a point, I'm sure you won't find it difficult understanding the monotonicity over an interval, right? So let's look at that. It has two simple points. The first one says that fx is said to be strictly increasing. I hope you remember this arrow up for increasing in interval a comma b, open interval a comma b, if f dash x, this is the important condition, if f dash x is greater than or equal to 0 and equality may hold for discrete values of x. Equality may hold for discrete values of x. And by the discrete values, we mean that the points where f dash x is equal to 0 don't form an interval. They must not form an interval or collectively long or large number of points, which is an interval only, right? So it is the simple point for strictly increasing. And the second point, again, fx is strictly decreasing if f dash x is less than equal to 0, and again this next condition is same, that equality may hold for discrete values of x only, right? So this point that discrete values of x, f dash x can be 0 and it should not form an interval. Let me try to explain it to you with the help of an example, with the help of an